So I think it's very interesting how the physical attributes of a device will manifest themselves with respect to the scattering matrix and its mathematical attributes. And we can look at the mathematical attribute of a matrix and discern physical descriptions of the device that it represents without having any other knowledge of the device other than its scattering matrix. We can extend this concept beyond simply the parameters or characteristics of match, lossless, and reciprocal. It turns out we can look at a scattering matrix and oftentimes discern the topology of its structure. How is it built physically? What must the underlying schematic, what its form must be? And of course, this is hugely helpful. We can go through, and if we have a certain scattering matrix that we device with a certain scattering matrix that we desire, we can look at the scattering matrix itself, and from that discern a lot about what the the resulting circuit that would realize it must exhibit the symmetries, the topology of that circuit. So let's go look at this, and I think this is a very important aspect of electrical engineering that is greatly ignored and shouldn't be, because it is so powerful and so interesting, and that is the concept of circuit symmetry. And so what is symmetry? You probably have some concept, most people do, of symmetry based on sort of aesthetic perception of structures and figures and rotations and reflections and such. And of course that things look nice artistically when we do that. But mathematicians have a way of trying to define numerically this concept of symmetry. So to mathematically describe the symmetry of an object, we have to use a branch of mathematics called group theory. And this was something that was developed way back in the 19th century, early 19th century, by a young French genius named Galois or Galois. I'm not sure exactly how to pronounce different ways there. My French is not great. I apologize. He was someone that was trying to understand the solutions to polynomials and third, fourth, fifth order polynomials, and which general solutions existed and which ones didn't. And so his group theory that he applied was to polynomial functions, or more specifically the zeros of polynomial functions. But it turns out we could apply them likewise to structures, physical structures, to evaluate their symmetry. So again, he was a young genius. He developed the whole branch of mathematics called group theory before he was 21. He was killed in a duel. So let's first look at an equilateral triangle. And of course, this is a very highly symmetric object by looking at it. That's maybe an adjective you would use to describe it. So it's obviously true, but how symmetric is it? How can we quantify it or compare its symmetry to other types of structures? So how would an equilateral triangle, the symmetry of an equilateral triangle, how would it compare, let's say, to the symmetry of an isosceles triangle or a rectangle and a square? How do we quantify the level of symmetry and describe it mathematically? So the first thing we notice is that the equilateral triangle has a plane of reflection symmetry, has bilateral symmetry. And of course, we've talked about this kind of symmetry with respect to odd-even mode analysis, and certainly this is the case for this equilateral triangle. Now what we're going to do is label each corner of the triangle, since they all really look the same. If we were to erase these numbers, we wouldn't be able to tell the difference between one quarter and the next here. And we're going to talk about the symmetry in terms of a permutation of these corners. So if we were to go through and reflect across this plane of bilateral symmetry, what we'd find is quarter 1 went to quarter 3, and quarter 3 went to quarter 1. And so we see this here. As we reflect across the plane of bilateral symmetry, we find 1 goes to 3, and 3 goes to 1. And so we're left with this situation here. Now, these two look different only because we've made these labels. Again, if we were to replace these numbers, we would find that we couldn't tell the difference between these two equilateral triangle. And of course, that is a statement of symmetry. I can reflect across this plane, and the resulting triangle is what we say congruent with the first one. They look exactly the same. We can't tell them apart if we hadn't have labeled the corners. So this is how we define the symmetry associated with this symmetric plane. We say, again, based on these labels, that we have a permutation. 1 goes to 3. All right, this corner goes over here. And of course, then 3 goes to 1, back over here on this side. This corner 2, of course, is the same after the reflection, before and after. So we write this mathematically as 2 going to 2. So on the permutation where 1 goes to 3, 2 goes to 2, and 3 goes to 1, that's a reflection across this plane of bilateral symmetry, we say that this object is congruent under this operation. All right, this operation is the reflection across this plane, and it looks the same after that operation. That is a statement of symmetry, that this plane is a plane of bilateral symmetry. Now, it turns out, of course, that's not the only plane of bilateral symmetry of an equilateral triangle. There's a plane that bisects each corner of the triangle, each of the 3 quarters there. So there's another bilateral plane of bilateral symmetry, reflection symmetry, which intersects the corner 3 right here. And in this case, if 1 reflects to 2 and 2 reflects to 1 and 3 of course stays the same, under this permutation we get this. Again, if we erased the numerical labels here, we would find that we couldn't tell the difference between these 2 equilateral triangles. These 2 triangles are congruent under this operation, a reflection across this plane, and therefore this is a plane of bilateral symmetry. Likewise, we could draw a plane through the corner that labeled 1, and we find if we reflect across this plane, 3 goes to 2, 2 goes to 3, 1 stays there. Here's the permutation description of that. We find under this operation we get this triangle. Again, this triangle is exactly the same as this one. It's the same orientation, same size, same everything. If I were to go through and erase the numeric labels, I would not be able to tell the difference between this and this. And so we say it has a symmetry such that the object is congruent under this operation, a reflection across this plane, and therefore this plane is one of bilateral symmetry as well. But wait, there's more, as they say. We can go through and have another operation where we take this equilateral triangle and we rotate it around exactly 120 degrees around its very center. And when we do that, corner 2 goes to corner 3, corner 2 goes to corner 3, corner 3 goes to corner 1, and corner 1 comes up to corner 2. And so this is the permutation that describes that operation, 1 to 2, 2 to 3, 3 to 1. And when we do that, we get this triangle over here. And we see again, they are congruent. They have the same orientation. I can't tell the difference between the 2 of them if we did not know the numerical labels there. And so we say that this object likewise has another form of symmetry, one where the object is congruent under this operation. This is not a reflection across a plane. This is a rotation around the center of the object. We can also do the same thing by rotating not 120 but 240, or we can look at it as rotating counterclockwise by 120 degrees. Either way, we come to the same result. We have a situation where corner 1 goes to corner 3 goes to corner 2, and corner 2 goes to corner 1. So this is the expression of the permutation, 1 to 3, 2 to 1, 3 to 2. And when we do that, we get this object here. The same object, congruent as what we started out with. Corner on the top, corner on left and right, flat bottom, it's all the same triangle there. And so we say this object is likewise symmetric with respect to this operation. It's congruent. I can apply this operation to this, and I get the same equilateral triangle as a result. And so now we've had 5 different operations that we can apply to our triangle and leave that triangle congruent with respect to the original. It seems to be unchanged even though we rotated or reflected. Now there's one more operation that we can do to this equilateral triangle, which will result in a equilateral triangle that is exactly the same, that is congruent under this operation. And this operation is pretty simple. It is essentially to do nothing. That corner 1 stays at corner 1, corner 2 stays at corner 2, and corner 3 stays at corner 3. So this is a description of that operation. And since we have done nothing to the equilateral triangle, it is congruent, both with respect to its original and its result. Notice that this operation would be true for any shape that we have. Every shape is congruent under this operation, and so we call this the identity operator of this group of operations. Now, this seems kind of silly that we put this identity operator in there, but group theory is a branch of abstract algebra, and what we need is an identity operator in that algebra. And this is true of all the algebras we have. If we have multiplicative algebra, we have an identity operator multiplying by 1. In addition, we have an identity operator, which is to add 0. And so in the case of operators which are rotations or reflections of this, we need an identity operator to complete the algebra, and that identity operator is shown here. Basically do nothing. We could factor this into two parts. We could go through and take a equilateral triangle and reflect across one plane, and then reflect back across again. And those two things would take us back to where we started. That would be equivalent to the identity operator. So it's sort of like saying 0 is minus 2 plus 2, or something like that. Or multiplying by 1 is multiplying by 1,000 and then dividing by 1,000. And so we need that identity operator to complete the abstract algebra of this group. So we have 6 operations under which this equilateral triangle remains congruent. 3 reflections, 2 rotations, and then of course the identity. 6 different operations where the equilateral triangle again remains congruent under those operations. Those 6 operations, the 3 reflections, 2 rotations, identity, form a group that's called the dihedral symmetry group D sub 3, or D3. It has order 6 because it consists of 6 operations. And you're like, why shouldn't it be D6? Actually, some people would describe this as D6, meaning that it has 6 operations. The definition of a dihedral symmetry group, though, is such that the subscript 3 you multiply, or any subscript you multiply 2, and that's actually the number of operations under which the object is congruent. Again, this would be 6. So let's look at the symmetry of some other objects. If we have an isosceles trapezoid, it has one plane of bilateral symmetry, just one plane, and it has no there's no rotation that we can do that would leave it congruent. If we rotate this around 180 degrees, we'd have a different object. We'd have the short side on the bottom and the long side on the top, and so that would not be congruent. We just have one plane of reflection symmetry. And so this symmetry group, the dihedral symmetry group D sub 1, has an order of 2 operators under which this is congruent: the reflection across the single plane of bilateral symmetry, and of course the identity operator gives its second element. A rectangle has D2 symmetry, D sub 2, and so there are 4 different operations that we can do to a rectangle to leave it congruent under those operations. There's 2 planes of reflection symmetry that happen, and then also we can go through and rotate it 180 degrees about its center. And then finally we have the identity operator, which gives us the order of 4 different operators that will leave it congruent. Again, one of 2 reflection planes, a rotation around 180 degrees, and then the identity operator. The square then has turns out has a symmetry group we call D4, D sub 4, dihedral symmetry group. Since it's 4, we multiply by 2. There's this group has order of 8. There are 8 different operations we can apply to the square, which will leave it congruent. There's one reflection plane here. There's one reflection plane there. There's a rotation, 3 rotations that will leave it congruent. And then the identity matrix. Let's see, that's 1, 2, 3, 4, 5, 6. Oh yeah, and then there's another plane of bilateral symmetry across the diagonal here and here. So there's 4 planes of bilateral symmetry reflection symmetry, we can rotate 90, 180, or 270. There's 3 rotations then, and then there's the identity. The identity operator you can think of as just rotating around 360. That's one way of looking at the identity operator. Anyway, we have an order of 8. And so mathematicians will look at this and say the isosceles triangle is symmetric with respect to a symmetry, a group D1, which has order of 2, where the square is symmetric under operations that have order of 8. There are 8 different operations. We can apply this. And so we would say that the square has a higher degree of symmetry than the isosceles trapezoid. The rectangle certainly is somewhere in the middle, and likewise the equilateral triangle with a order of 6 is between the isosceles and the rectangle itself. By the way, I should point out the object that two-dimensional object with the highest level of symmetry is a circle, and essentially the order of the group that describes the symmetry of a circle is infinite, because there's an infinite number of planes of reflection symmetry, and there's an infinite number of rotation angles around the center that you can rotate and leave the circle congruent under those rotations. So you're thinking to yourself, this is all very fascinating, and of course it is fascinating, but what does it have to do with electrical engineering? Well, it turns out many of the circuit structures that we make in electrical engineering have a high degree of symmetry. Again, we talked about this with respect to odd-even mode analysis. And so let's look at a 4-port device, a simple 4-port device here. And we look at it, this one, it has a single plane of reflection symmetry. 200, if we reflect across this plane, this 200 ohm goes to here, and 200 ohms goes here. The 50 ohm resistor just flips, so it remains the same likewise for the 100 ohm. And so the labels, port 1 and port 2 and port 3 or port 4, what we could do is simply interchange the labels without really changing the structure of the device because of this symmetry. And so if we relabel port 1, if port 1 goes to port 2, and port 2 goes to port 1, and port 3 flips over to port 4, and port 4 goes to port 3, when we're done, we have the same circuit as what we started. If we erase the port labels, we couldn't tell the difference between the original circuit and the new circuit, quote-unquote new circuit, after reflecting across this plane of bilateral symmetry. Likewise, we'd have a second operation that we could do to the circuit, which would preserve the circuit and be congruent under that operation, and that is the identity operator. So this has a structure. The circuit structure is described symmetry as the dihedral group 1, d sub 1, which has a order of 2 different operations, which leave it congruent when again rotating across this plane of bilateral symmetry. So this circuit itself can be described group theoretically. So here's another 4-port device, and it has the same level of symmetry, this d sub 1 symmetry. There's 2 operations that will leave it congruent. Really, this is the same kind of circuit as the one we just shown. The reason I put it in here is because this one has a plane of bilateral symmetry that runs horizontal. And so 50 reflects down to 50, 50 up here, and then again we simply rotate the resistors, 100 and 200 ohm resistors, and they remain the same. 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. And when we do that, we find we have the same circuit as we started with. We couldn't tell the difference if we erase the port definitions. They look precisely the same. 50 ohm resistor here, 50 ohm resistor there, 100 ohm on the left, 200 on the right. That's true after applying each of these 2 operations, and therefore this is described with a group of order 2. So let's look at this 4-port device. This has a different kind of symmetry. It's more symmetric. We have a plane of bilateral symmetry here. If we reflect 200 ohms over here and 200 ohms over there, it'd be the same circuit. But we have a second plane of bilateral symmetry that goes horizontally. 50 ohm reflects to 50 and then back again. So in this case, unlike the last case where we had 3 different resistor values, now we just have 2 different resistor values in this structure. By the way, I've written this as a 4-port device using simple resistors. Of course, we could use more complex values in here, more complex structures and reactive elements, and ultimately we'll talk about links of transmission line that preserve this symmetry. But I'm just trying to make a simple 4-port device where it's obvious to see this symmetry of this structure is that of a rectangle. You can kind of see, just like the sides, this side and this side have the same length, this side and this side have the same resistance. The top and the bottom have the same length, the top and the bottom have the same resistance there. And so, like a rectangle, this exhibits a symmetry associated with the d sub 2 group, a group which has an order of 4 different operations we can apply to this circuit and leave it congruent under those operations. One, of course, is the identity matrix, or the identity operation, to do nothing, and then we have 2 operations which reflect over the 2 planes of bilateral symmetry. The last operation is a rotation operation. If we take the center and we rotate around the center 180 degrees, port 1 will rotate to port 4, port 4 will rotate to port 1, port 3 to port 2, and port 2 to port 3. And so that's defined by these sets of permutations. We look at this 4-port device, and this is becoming even more symmetric. Notice in this case it has the symmetry associated with a square. Every side of the square has the same length, and notice every side of the circuit has the same resistance of 50 ohms that we have. And so there's just one resistance value for all 4 of the resistors here, but that gives us an incredible level of symmetry. There are 4 planes of bilateral symmetry, 1 vertical, 1 horizontal, and additionally 2 diagonal planes that we can rotate across and remain congruent. Now, if we rotate across these diagonal planes, it at first doesn't look like they're exactly congruent because, of course, I didn't draw the circuit itself to be literally square. But with respect to the resistance values, the resulting circuit would be identical. It's just the fact we have a longer wire here than we have here, but otherwise it's the same. At any rate, this has the symmetry associated with the d sub 4 dihedral group, which is order 8. There are 8 different operations that we can do which will leave this circuit congruent. 4 reflections across the 4 planes of symmetry, and then 4 rotations. We can take the center and we can rotate 1 to 2, 2 to 4, 4 to 3, 3 back to 1, essentially 90 degrees rotation, or we could do 180, or we could do 270. So there's 3 different rotation angles there, in addition to finally the identity operator being the 8th member of the group. So for completeness, we can talk about 3-port devices, and in this case, again, this is sort of a simple circuit structure that hopefully will show you it has the same level of symmetry as an isosceles triangle. In the isosceles, 2 of the sides have the same length and the third has a different one. In this case, 2 of the sides have the same resistance, and of course this then has a different one. There's 2 different resistance values associated with this structure, and there's simply one plane of bilateral symmetry, and therefore this is a d sub 1 symmetry, and 2 operations that leave it congruent. One, the reflection across this bilateral, this reflection symmetric plane, and then the of course the identity operation. Another 3-port device here. In this case, it has the same symmetry as our original equilateral triangle. Each of the 3 has the same sides, have the same length. In this case, each side has the same resistance value here. And so we understand the symmetry associated with this. It's the D3 symmetry, which has order of 6 different operations that we can do to this, which will leave the structure, the circuit structure, unchanged, congruent. 3 planes of reflection symmetry, 2 rotation angles of 120 degrees, and finally the identity operation. So as fascinated as you are by this, you may still be wondering how is this useful to you as an electrical engineer. And so let's see how this is going to be helpful to recognize the symmetry associated with a circuit. Let's go back and look at this circuit, which has a fairly limited amount of symmetry. Notice again we have 3 different resistor values here, not 4, but we only have 3. And so that results in one plane of bilateral symmetry, like the isosceles trapezoid. So the group that describes this symmetry has an order of two different operations under which the circuit is congruent. One of them is identity, which is very interesting. So let's look at the operation, the other operation, which is the reflection across the plane of bilateral symmetry. So port 1 reflects over to port 2, and 2 goes to 1. Port 3 reflects to 4, 4 goes back to 3. And so this is the resulting circuit that we get. Notice the circuit itself is congruent after this operation. I have 50 on top, 50 on top, 100 on the bottom, 100 on the bottom, 200 on the left, 200 on the left, 200 on the right, 200 on the right. Really, this looks no different, and if we had gone and taken our pencil and erased port 1 and wrote port 2, erased port 3 and wrote port 4, erased port 4 and wrote port 3, and then likewise port 2 and made it port 1. Physically, we say we rotated across this plane of bilateral symmetry, but we really can't tell the difference between that and simply renaming the ports. So think about what this means with respect to our standard characterizations of a multi-port circuit. Scattering matrix, impedance matrix, admittance matrix. If I can go through and simply rename port 1, port 2, and rename port 2, port 1, and not change the circuit in any way, what that means is the resulting value of S11 and S22 must be the same. Since the circuit is the same, regardless of whether I call that port 1 or 2, the resulting parameters must be the same, and therefore S11 and S22 must be equal to each other. This is a symmetry argument that we have. Likewise for Z11 and Z22, or Y11 and Y22. Also, due to symmetry, because 1 goes to 2 and 2 goes to 1, we could take the scattering matrix S12, and by symmetry arguments, we could say for this D1 symmetry that S12 must be equal to S21. Again, we just go through and call port 1 port 2 and port 2 port 1. Otherwise, we haven't changed the circuit. Since we haven't changed the circuit, we're going to get the same result for the scattering parameter. And so we know that S12 is equal to S21, likewise for impedance and admittance parameters, for example. So we also found that this circuit was congruent under the operation of reflection, such that port 3 permeated to port 4 and 4 to 3. Again, essentially we're renaming the ports 3 to 4 and 4 to 3 there. Since the circuit itself does not change, we have to get the same result with respect to the scattering and impedance parameters with respect to those ports. And so we can calculate the value of S33 and then erase that port name and call it port 4 and recalculate then the scattering parameter S44, but it's going to be the same. It's the same circuit. So S33 is equal to S44, likewise for impedance and admittance. And also then we take S43, 4 goes to 3, 3 goes to 4, and so S43 must be equal to S34. And so we put all the pieces together. 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3, and we come up with this set of equations now for that circuit, circuit with D1 symmetry. We know the scattering parameters of that circuit because it's symmetric. It's in symmetric arguments alone that these equations must be valid. This is true for the scattering matrix and the impedance matrix and the admittance matrix. So this has nothing to do with matched. It has nothing to do with lossless. It has nothing to do with really with reciprocity, although some of these things are true also because of reciprocity. Notice that we have a situation now where let's see where I've lost myself. S43 is equal to S34 there. And so that's because of reciprocity. And so, and again, we add these and we add these equations as well. So we have to be careful here. 1 goes to 2. So this S31, this one goes to 2, but also 3 goes to 4 in that permutation, and so this 3 has to go to 4. In other words, S13 is equal to S24. You can't rotate port 1 to port 2 without also rotating port 3 to port 4. So we can't make the argument, and sometimes students do, that S13 is equal to S23, for example. We can't. 1 goes to 2, but also in that same reflection process, 3 reflects onto 4. So S13 is equal to S24. S31 is equal to S42. 3 goes to 4, 1 goes to 2, for example. And so we have these equations as well. So we take all those equations that we just determined by applying our knowledge of symmetry and group theory, and we see that a 4-port device which has this fairly meager level of symmetry, this D1 symmetry, one plane of reflection symmetry there, we find that the resulting scattering matrix must have this form. And we count them. There are 1, 2, 3, 4, 5, 6 different independent scattering values of the 16, and I've tried to color code them so you can see them. There's 2 here, 2 there, 2 there, 2 there, 2 green ones, orange, and I lost track anyway. They go through and did I say 8? There are 8 pairs of 2 that form this 16 elements of the scattering matrix there. Oh, by the way, this form is likewise true for impedance and admittance matrix. And notice again, we haven't applied anything to do with reciprocity here. This is simply strictly applying a symmetry argument to a structure with D1 symmetry. Now, if we also apply reciprocity, again, which is almost always the case, it's hard to mess up reciprocity, we can add 2 more equations, and that is S13 is equal to S31. There's no symmetry argument for this to be true. This is exclusively a reciprocity argument. It's also for S41 and S14 must be equal to each other by reciprocity, not by symmetry. But we add these 2 reciprocity equations to our previous 8 symmetry equations, and now we have a situation where we have a scattering matrix of this form. And in this case, there are just 6 independent elements. All right, there are 2 here and 2 here, and then 4 here, and then 4 here. And so 6 all together. So why do we care about this? Well, it makes a big difference if we're trying to complete the scattering matrix of some circuit. So we have a circuit and it has, again, a relatively low level of symmetry, this D1 symmetry, just one plane of reflection symmetry. But instead of having to go through and calculate 16 different elements, it turns out we simply need to determine 6 different scattering parameter values. Likewise, if we're doing impedance or admittance, just 6 parameters. Once we have those 6 parameters, we can fill out the rest of the matrix without doing any more work. Or we might want to go ahead and try to evaluate those other elements as a sanity check. When we get through, if we evaluate all 16, we can look to see if our resulting scattering matrix has this form, these elements that must be equal to each other. If it's not, we know we've made a mistake. So we can continue this for all of the structures that we previously analyzed with respect to their symmetry, exhibiting different levels of symmetry with different symmetry group of different orders there. And so we looked at this structure, this circuit, and we found that it had similar symmetry, D1 symmetry, a plane of reflection symmetry. And if we go through and do the permutation 1 to 3, 3 to 1, 4 to 2, 2 to 4, and so forth, and also apply reciprocity to it, we find we get a scattering matrix, or equivalently an impedance or admittance matrix of this form. Again, there's just 6 independent values. Once we find those 6, we can populate the remainder of the scattering matrix. We can stipulate all 16. So continuing, if we have a 3-port device with D1 symmetry, just one plane of bilateral symmetry, if we apply the symmetry arguments for those, we can find it reduces down to this form. There are 1, 2, 3, 4 different values in this 3x3 matrix. So once we find those 4, we can populate the remaining 5 scattering parameters or admittance or impedance values. Going to a circuit of a higher level symmetry, D2 symmetry, D sub 2, like a rectangular, if we go through and use all the permutations, we can show that the resulting matrix, impedance or scattering or admittance, must have this form. If it's likewise reciprocal, it turns out that And I think even if it isn't reciprocal, and this is the case, there are simply 4 independent values for this level of symmetry. All right, the diagonals all have to have the same value. There's 4 there, the blue ones, that have the same value. There's 4 ones there, the green ones, and then the cross-diagonal element must have the same values. There's red ones there. 4 independent values. Once we find the 4, and notice those 4 permutate in terms of the columns. Once we find one column, in other words, of our scattering matrix, then we know all of the elements of that scattering matrix. So going back to a 3-port device, which has D3 symmetry, that of the equilateral triangle, if we go through and apply all the permutations, we can show that the resulting scattering or impedance or admittance matrix must have this form. And this is a very simple form. There's simply 2 elements required to populate the entire scattering matrix. Once we know the diagonal value and we know one of the off-diagonal values, then we can populate the entire scattering matrix. So this is very simple. Find 2 values and then we can populate the whole thing. Or like I said, we could go through and do the evaluation and try to find all the scattering parameters in the scattering matrix and then check to make sure that they have a structure that is reflected by this structure. Again, the diagonal elements are the same and all the off-diagonal elements are likewise equal to each other. If we extend that to a 4-port device with D4 symmetry, this is a very high level of symmetry, that of a rectangle, 8 different operations that we can apply, and we'll leave the circuit congruent. As we might expect, we find that there are only 2 different independent values in the resulting matrix. Here I show an admittance matrix, but this would likewise be true for a scattering matrix. All the diagonal elements are the same. If I want one diagonal element, I know all of them, and all the off-diagonal elements are the same. Once I know one diagonal off-diagonal element, I know all of them. And so to find the full scattering matrix, for example, of a 4-port device with this level of symmetry, we would only need to find S11 and S21, and then we could fill in the remainder of that scattering matrix. So here's a result that I think is very interesting and I think really shows the power of using symmetry in electrical engineering. Recall that we went through and we talked about this idea of having a device that was matched, lossless, and reciprocal. We saw that that can exist for a 2-port device and a 4-port device, but not for a 3-port device. By the way, it can also exist for a number of ports higher than 4. So really 3 is the only one that a matched lossless reciprocal device cannot exist. For a 4-port device, though, the solutions were somewhat limited. We had 2, one we called the symmetric form and the other we called the asymmetric form. With the symmetric form for a 4-port matched lossless reciprocal device, we got this result here, where the magnitude of alpha squared plus the magnitude of beta squared must be equal to 1. It's constrained by this. So let's compare this matrix to forms of our symmetric circuits. Again, we call this the symmetric solution, and now we're talking about symmetry in circuits, but these are different things. So I call it the symmetric form in quotations here, meaning this solution. Call it solution A. Compare it to the scattering matrix for our different symmetrical solutions. So when we compare the two, the quote-unquote symmetric solution that we had for a matched loss reciprocal 4-port device, and we compare that to the results we got for different levels of symmetry, we find that the structure of this scattering matrix is identical to the scattering matrix we got from a structure that had D sub 2 symmetry, a structure that really had the same symmetry as a rectangle. And so a 4-port device of this symmetry will result in a scattering matrix which has the same form as the symmetric solution for a matched lossless reciprocal 4-port device. So that leads to a question. Does this mean that a matched lossless reciprocal 4-port device with this symmetric solution must exhibit this level of symmetry? And that's exactly what it means. We have determined that we can find a matched lossless reciprocal 4-port device, one that has this scattering matrix of this form. Now we've shown that that circuit must have a level of symmetry described by this dihedral 2 group, this order of 4, the same symmetry as a rectangle. The circuit that we construct to satisfy the scattering matrix, now we know the essential symmetric structure of that circuit. So let's look at the quote anti-symmetric solution. There was another solution, remember, for the lossless reciprocal matched four-port device. We call that the anti-symmetric form. Again, it has alpha and beta, but we have minus beta. Again, alpha squared plus beta squared must be equal to 1 for it to be lossless here. And if we look at this structure and compare it to the structure of a scattering matrix for a circuit that exhibits D1 symmetry, a single plane of bilateral symmetry, we find that they have the same structure there. These two values are the same. These two values are actually these, and these are the same. These are same. Those are the same. And so it turns out that this maps into the same matrix structure there. And so what we find is if we want to build a matched lossless reciprocal four-port device which exhibits a scattering matrix of this form, we need to build a circuit, a four-port device that exhibits this D1 symmetry, a circuit that has one plane of bilateral symmetry. So I don't know what it looks like. It depends on what you're trying to do with these scattering parameters here, but we do know it must exhibit this level of symmetry in order to create the proper scattering matrix for this solution. So here's a couple examples of this. These are microstrip drawings of four-port devices. So this is the top side edge. Should be a ground plane underneath. Port 1, port 2, port 3, and port 4. If we look at this, we notice there's one plane of bilateral symmetry right through there. And so this is the same symmetry as that of an isosceles trapezoid. And we know the resulting scattering matrix, if it's matched lossless and reciprocal, will be that of the anti-symmetric solution. And in fact, it is. So this is a useful device. It's called a ring hybrid or 180-degree hybrid. It's a coupler that we'll learn about you can learn about in the coupler section there. If we go to another device, this is a matched lossless reciprocal four-port device. Again, this is shown in terms of its microstrip design. This is topside edge. The different widths of lines have different characteristic impedances. We show the line lengths lambda over 4. That shows up all the time. If we look at it, I mean, it basically looks like a rectangle. I mean, you can kind of see two sides are the same here and here. Two sides are the same here and here. And so it has a symmetry associated with D2, the dihedral d sub 2 symmetry, and therefore has order 4. We know what the resulting scattering matrix must look like. If it's matched lossless reciprocal, we know then that it must be the quote-unquote symmetric solution for that matched lossless reciprocal four-port device. So again, we look at that and say, well, gosh, this must have a circuit of this level of symmetry. And in fact, here is one circuit that will match lossless reciprocal for the symmetric solution, and it sure enough has two planes of bilateral symmetry and one of rotation around 180 degrees. So these last two pages, I just show a summary of all the results. I never really talked about a two-port device, but you can have a two-port device that has one plane of bilateral symmetry. That's the highest level of symmetry you can get. And if that is the case, then we end up with this 2x2 matrix. The diagonal elements are the same, and the off-diagonal elements are the same. And then continue with the structures that we talked about before. The equilateral triangle, the isosceles trapezoid, two forms, both with a vertical and horizontal plane of reflection symmetry. And then the remainder, D2 symmetry, D3 symmetry for the equilateral triangle, and then finally D4 symmetry for the rectangle, which is the highest level of symmetry we have for a four-port structure, just simply two values that we need to find. So try to put all the results here in one place so you can look at them. Again, the power in this, there's a couple of things. One is that if we're trying to find the scattering matrix of a device, if we recognize the symmetry of that device, we can reduce greatly the number of parameters that we need to find. Or we can go ahead and calculate each of the elements in the scattering matrix and then use it as a sanity check. Does the resulting scattering matrix exhibit the symmetry that it must? If it doesn't, you've made a mistake, because it must exhibit those levels, that symmetry, in the results that we've shown here. The other thing so powerful about this is you can go through, and if you have a device that you are hypothesizing, and you have a scattering matrix, like a device that has these scattering parameters here that, maybe it's matched lossless or whatever, and have certain values for the scattering parameters, you can write them all down and look at them and say, okay, what is the structure of the scattering matrix? What is the symmetry associated with the scattering matrix? And if you can identify that symmetry, all of a sudden you know the topology of the circuit that you must create. You know how many planes of symmetry or rotation symmetry must be in that circuit to bring about the scattering matrix or impedance matrix that you're trying to achieve. So I think symmetry, again, is a very interesting and very important and powerful tool in electrical engineering, and unfortunately it's one that is not widely understood or taught. But an engineer that can master them, I think, will find that it will be very useful in their career.